So then I'm looking at where secant theta equal to -2. So again, I know secant is reciprocal of the cosine. So really we were looking at to see where is cosine equal to -1/2. So remember, cosine is negative in quadrants 2 and 3. So then what are my angles going to be in quadrants 2 and 3? It's going to be where theta is equal to what? So what's the angle going to be in quadrant 2? Where is cosine equal to -1/2? At 2 pi over 3, and then down there in quadrant 4 it would be, 3, it's going to be 4 pi over 3. So there's your two solutions. Okay, so that was the first day. Look at equation number 2. You have an equation with all cosines in it. Is it a linear or quadratic equation? Quadratic, because you have a cosine to the second. How do you solve any quadratic equation? We always try and solve it by factoring. So what do we want to have on one side of the equation? We want to have a 0. Remember, you never ever will take a trig function and divide it out of the equation. I know the temptation for some of you may have been to divide everything by a cosine. When you have that instinct, that is a wrong instinct. What you should be thinking, okay, well, if I want to do this, that's going to be a GCF factoring problem. Move it to the other side and then do your GCF factoring. Because what can I factor out of both sides? I can factor out a cosine. So 2 cosine theta minus 1 is equal to 0. So then I can take each factor and set it equal to 0. So then where is cosine equal to 0? Cosine's equal to 0 at pi over 2 and 3 pi over 2. Remember, it's a quadrantal. It's down there on the y-axis. And then cosine is equal to 1/2. Remember, cosine's positive in 1 and 4. So the angle is going to be at your what? Pi over 3 and 5 pi over 3. So any questions on the second one? So let's take a look at number 3. What do you think you're going to have to do in number 3? Sub in, if you need to, do that substitution. You can plug in x for sine. And then what algebra are you going to have to do on this equation? We're going to do what? Factor it. It's a quadratic equation. So you guys go ahead and factor. So where is sine theta minus 1 equal to 0? 2 sine theta plus 1 equals 0. So next I need to look, where is sine equal to 1? So where is sine equal to 1? Pi over 2. So there's one solution. Next I want to know, where is sine theta equal to -1/2? So remember, sine is negative in what two quadrants? Sine is negative down there in quadrants 3 and 4. So then the angle down there in quadrant 3 is going to be at 7 pi over 6 and 11 pi over 6. So any questions on the first 3? First 3 is really going back over what we did the first day when we were dealing with the linear and the quadratics. Now let's take a look at number 4. Number 4 is a lot different. It is a quadratic equation, but you have a problem. What's the problem in number 4? 2 different trig functions. So as we talked about, when you have 2 different trig functions, the goal is to try and write it so that it's in the form of just one trig function. So again, you've got this trig function to the second power. So remember, anytime you see those trig functions to the second power, again, the cosecant you're kind of stuck with. You don't want to rewrite this as 1 over sine, because that's not accomplishing your goal of trying to change this into one trig function. But when you see a trig function to the second power, zero in on those Pythagorean identities, because those are all to the second power. So is there a way to rewrite cotangent squared and bring in a cosecant? And there is, because remember, cotangent squared is equal to cosecant squared minus 1. So I can change cotangent squared into cosecant squared theta minus 1. Minus cosecant theta equals -1. So again, your goal is to try and get at least the same trig function in the same equation. So by my Pythagorean identity, I can change that cotangent squared into cosecant squared minus 1. So now what kind of equation is this? Is this a linear or a quadratic? quadratic. So what do we want to have on one side of the equation? We want to have a what? 0. So I'm going to add 1 to both sides. Well, what happens when I combine my like terms of a negative 1 plus 1? That's going to go to what? 0. So I'm left with a cosecant squared theta minus cosecant theta equals 0. So now how do we solve this quadratic? What factoring technique am I going to use? I'm going to use what? Take a cosecant out. Use your GCF. So now I'm going to set my cosecant theta equal to 0. Cosecant theta minus 1 equal to 0. Is there a place where cosecants equal to 0? Let's talk about that for a minute. Well, cosecant's reciprocal of the what? Cosecant's reciprocal of the sine. So you can look at this as where sine is equal to, what's the reciprocal of 0? Undefined. Is there any place on the unit circle where sine is undefined? No. So there's going to be no angles coming from that particular factor.
Should we write
no? Just disregard it. Now, if I come up with the next factor and there's no solution, then you would write no solution. So now I'm going to look to see where is cosecant theta equal to 1 at pi over 2. Had I not had a solution for that second factor, then you would have written no solution. But you do have a solution of pi over 2. All right, so any questions on number 4? Now let's take a look at number 5. Well, number 5, I do have just one trig function. That's a cosine. But the problem is, I've got this cosine of 2 theta. Would the multiple angle work? No, because you have that cosine squared. But what can you do with this cosine 2 theta? What trig identity substitution can we do? The double angle, exactly. Now remember, with cosine, you've got 3 variations, 3 choices of the cosine double angle. Which one would make the most sense to replace in this particular equation? 2 cosine squared minus 1, exactly, because you don't want to bring in a sine because you already have a cosine squared in here. So we're going to replace that cosine of 2 theta. So we're going to change that into 2 cosine squared theta minus 1. Then I can do what? I can combine. These are like terms. So what's cosine squared plus 2 cosine squared going to give you? 3 cosine squared theta. Any thoughts on what you want to do next? You can if you want to get rid of the fraction in the equation, you can multiply everything by a 4. So I'll give you 12 cosine squared theta minus 1 is minus 4. Don't forget to multiply the 1 by 4 is equal to 5. Again, if you want to get rid of the fraction in the equation, you can use your LCD trick and multiply everything by a 4. You don't have to. You could left the 5/4 in here. Now what are you going to do? You're going to subtract 5?
We're going to do plus 4 plus 1 and do square.
Yeah, because remember, this is a quadratic. So the problem is if you subtract the 5, you're going to kind of be stuck. There's no factoring to be done. But remember, another technique you have to solving quadratics is get that x squared or cosine squared by itself and use the square root method. So I'm going to add 4 to both sides. So 12 cosine squared theta is equal to 9. Then what? Divide by 12. Can you reduce 9/12? That's going to be 3/4. Then what? Square root. What do you have to remember to put in front of the square root when you do square root? Plus or minus. What happens, remember, when you have a fraction under a radical, you take the square root of the numerator and you divide it by the square root of the denominator. So what does square root of 3/4 actually reduce to? That reduces to the square root of 3 over 2. So don't forget, when you have a fraction under that radical, you take the square root of the numerator and you divide it by the square root of the denominator. So what angles are we looking at? Pi over 3, all of them, right? Because we're looking at plus or minus. So then theta is going to be equal to pi over 3, 2 pi over 3, 4 pi over 3, and then 5 pi over 3. So you actually have 4 answers to that one. Oh no, it should be your pi over 6s. Pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Sorry about that. Yeah, your pi over 6s. That's where cosine is equal to square root 3. So all your pi over 6s, your pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Any questions on recognizing? Because that's now the thing. They're all going to be jumbled together. So now what you have to be able to do is recognize what to do when. What do you think on number 6? It's going to be your multiple angle, exactly, because again, you've got that 4 theta. Is this a good news or bad news situation? Good news, because you have to consider. So you guys go ahead and try number 6 on your own. And when you were generating the angles, but then when you reduce the fractions, the denominators are not necessarily going to be the same. Okay? So like I said, after you take it out to that third angle and you notice that there's that pattern, use it to help you find all the others. 2 pi over 12? So when I plugged in 0 for k, 2 pi over 12 was my original angle here. What I did, remember my original angle was pi over 6 plus pi over 4k. So again, I just changed 2 pi over 12. It depends on how you treated that original general solution. I got common denominators before I get started, so that way I'm not constantly finding common denominators. If you did not change pi over 6 into 2 pi over 12, you would have originally gotten pi over 6 as the first angle anyway. Depends on, I just always get these common denominators to start, so I'm not constantly finding LCDs over and over again. Any other questions on that one?
Tan of pi over 6 was pi over 3.
It is right here.
Oh, okay.
And then I have to divide by 4, or multiply by a 4th, so I multiplied this by a 4th.
I multiplied by the 4th.
Yeah. So then that's going to give me 2 pi over 12, which is where I got the 2 pi over 12 plus pi over 4k from. Okay? So that's where the 2 pi over 12 came from. Right? Any other questions? Okay. So any other questions on this one? Any other questions on this one? Okay. Let's take a look. I'm going to get another sheet of paper since we don't have it. What about the number 7? What type of equation do we have in number 7? Well, it's the multiple angle type, correct? Because it's theta over 3. So is it the good news or bad news?
Good news. Bad news.
Why is it bad news? Because you got to do both of them, exactly. So it's a bad news situation because, again, you've got to figure out where is cosine equal to square root 2 over 2. So where is cosine x equal to square root 2 over 2? So what are your angles going to be? Your angle's going to be at what? Pi over 4 and 7 pi over 4. So now remember, you have to consider both of them. So we have to take theta over 3, set it equal to pi over 4, plus 2 pi k. Then what do? Multiply by 3. So again, theta is going to be equal to 3 pi over 4 plus 6 pi k. So what's the one and only angle that's going to fall between 0 and 2 pi for this one? It's going to be at what? 3 pi over 4. Because if you plug in a 1 for k here, you're going to get an angle larger than 2 pi. But like we mentioned, this is your bad news situation. You've got to consider that 7 pi over 4 as well. So theta over 3 is equal to 7 pi over 4 plus 2 pi k. Exactly, because when I multiply by 3, this is going to be 21 pi over 4. Is 21 pi over 4 already larger than 2 pi? Yes. So you only have one solution there, 3 pi over 4. You guys go ahead and try the last one for me on your own. Probably need a separate sheet of paper on that one. So are we good on those questions? All right. So guys, you have to be really careful. I can't emphasize this enough for the test on Friday. As you can see, if you mess up going back to the unit circle, if you pick the wrong angles in the very beginning, the whole thing is wrong. I mean, in other words, you're not going to come up with the correct solutions. So you've got to make sure for Friday, guys, this test will be an utmost disaster if you do not know that unit circle and those inverse values. You've got to make sure you study and go back over that unit circle, because otherwise this test is not going to be pretty. So make sure you go back and you know your unit circle for the test on Friday, which again, if you need to redo the unit circle mini quiz, you can